Hey everyone, welcome back to The Explainer. Today, we're diving straight into section 5.6 of our source material, which is all about model performance assessment. We spend all this time building these incredibly complex statistical models, right? But how do we actually know if they work? Let's find out. You know, the famous statistician George Box once hit the nail on the head when he said, "All models are wrong, but some are useful." And honestly, that's the whole crux of the issue. Building the model, that's just half the battle. Since every model is just a simplified approximation of reality, our real job is proving whether or not it's actually useful for what we're trying to do. So that leads us right to the million-dollar question. How do we know if a model is useful? What does success even look like here? Well, the ultimate proof comes down to how the model handles brand new, totally unseen data. Data it has absolutely never encountered before. Okay, let's dive into this. Here's our roadmap for today's explainer. First, the ultimate test. Second, grading regression models. Third, the confusion matrix. Fourth, precision versus recall. Fifth, accuracy and cost. And finally, the ROC curve and AUC. All right, kicking things off with section 1, the ultimate test. So think of your data in two completely separate buckets. First, you've got your training set. This is the open book. It's the data your algorithm has already seen and learned from. But, acing the test when you've already studied the answer key isn't exactly impressive, is it? The true final exam is the test set. That's the sealed envelope. If our model can successfully predict outcomes on this unseen data, it proves it generalizes well. And that generalization is absolutely crucial. It's the ultimate proof that your model is actually ready for the real world. Moving right along to section 2, grading regression models. When we're predicting continuous numbers, our go-to metric is usually mean squared error, or MSE. Now, if you look at how a model fits the data, you might see a smooth, generalized trend, or you might see a wild, erratic jacket fit. We calculate the MSE for our training data, and then completely separately the MSE for our unseen test data. Here's the kicker. If your test MSE is substantially higher than your training MSE, you've likely hit that jagged reality. That is a classic symptom of overfitting. It essentially means your algorithm didn't learn the underlying patterns at all. It literally just memorized the training answers. Not great. Which brings us to section 3, the confusion matrix. Now, grading gets quite a bit messier when we stop predicting continuous numbers and start sorting things into distinct categories, classification problems. And for that, we use what's called a confusion matrix. Honestly, it's a brilliant little tool. It's simply a cable that summarizes exactly how successful our model is at predicting examples across different classes. Let's make this concrete with a classic binary problem: spam versus not spam. If an email is actual spam and your model correctly flags it as spam, boom, that's a true positive. If it's a normal email and it's predicted as normal, that's a true negative. But the errors are where things get really interesting. A false positive is when the model predicts spam, but it's actually a completely normal email. And a false negative is when it predicts normal, but it's actually a pesky spam message slipping through. Next up, section 4, precision versus recall. These two metrics, precision and recall, tell very different stories about our model's performance. You can think of precision kind of like throwing darts. Out of all the darts you threw, meaning all the positive predictions your model made, how many actually hit the target? Recall is totally different. It's more like a magnifying glass. Out of all the actual, true positive examples that exist hidden out there in your test set, how many did your model successfully uncover? To illustrate this, think about searching a huge database. Precision is the proportion of actually relevant documents within the specific list of results you just got handed. Recall, however, is the ratio of those relevant documents you found compared to the total number of relevant documents that exist in the entire filing cabinet. And the reality of machine learning? You almost always have to choose between the two. It is incredibly hard to perfectly optimize for both high precision and high recall at the very same time. Let's head into section 5, accuracy and cost. So, accuracy. It is probably the most straightforward metric we have. It's just the number of correctly classified examples divided by the total number of examples. Simple, right? Well, it works perfectly, but only if making an error across all your different classes is equally important. And as we know, in the real world, that's rarely the case. Let's go back to our email example to see why. Think about weighing these two specific outcomes. A false positive means a friend sends you an urgent email and your model aggressively junks it. That's a huge problem. A false negative just means a random spam message slips into your inbox. Annoying? Sure. Catastrophic? Not really. Missing a real email carries a much, much heavier weight. Those errors are definitely not created equal. Because of that imbalance, we need a way to explicitly tell our model which mistakes to avoid the most. That's where cost-sensitive accuracy comes in. With this approach, you assign a specific cost, basically a heavier mathematical penalty, to the worst types of mistakes before you calculate your accuracy. By making the cost of a false positive extremely high, you're forcing the model to try significantly harder to avoid throwing away your friend's email. And finally, Section 6, the ROC curve and AUC. ROC stands for Receiver Operating Characteristic. Now, to even plot one of these, your model needs to output a confidence score, not just a hard classification. By adjusting the threshold for that score, kind of like sliding a dial up and down, we change how aggressively the model filters. We then plot the true positive rate against the false positive rate across every single possible threshold setting. What we're really looking for here is the area under the curve, or AUC. An AUC of exactly 0.5 gives you a straight diagonal line. That means your model is literally no better than a random coin flip. If your AUC drops to, say, 0.4, well, something is fundamentally broken. What we really want is for that curve to push way up into the top left corner. If Flawlessly Perfect Classifier would have an AUC of exactly 1.0, giving you a true positive rate right up near 100% while keeping the false positive rate down near 0. We've covered a lot of ground today, right? From the final exam of the test set to the intricate balancing act of precision, recall, and ROC curves. So I want to leave you with this final provocative thought. If all models are mathematically wrong, like George Box reminded us at the very beginning, what is the right metric for your specific problem? The biggest takeaway here is that choosing the correct scorecard, whether that's raw accuracy or a highly tuned, cost-sensitive matrix, is absolutely just as important as building the model itself. Thanks for joining me for this explainer, and I'll catch you next time.